Welcome, everybody. I want to give an example linear programming application to cutting paper rolls. So you're in charge of a factory, and you build these paper rolls. So these reams of paper that I guess I remember from elementary school, and you can sort of like unroll different colored papers for making posters and such. So all of your rolls are 3 meters wide. So here's our paper roll. You could sort of unroll it, and this, maybe this red paper comes out, and we can use it to make a pretty poster. And the width of each roll is 3 meters, which is 300 centimeters. Okay, so what's an elementary school in Fort Collins? Help me out.
Laurel Elementary.
Laurel, thanks. I think that's the closest to my house. So Laurel Elementary School puts in an order. They want to order rolls of certain widths. So they don't want all of their rolls to be 3 meters long. They want a roll that's only 135 centimeters wide. Okay, so how many rolls do they want that are 135 centimeters? Well, they want 97 such rolls, okay? But then they also want 610 rolls that are 108 centimeters wide, and they want 395 rolls that are 93 centimeters wide, etc. You want to produce these rolls, this order, using as few 3 meter long rolls as possible. So all you produce is these 3 meter wide rolls, and you want to chop up these 3 meter wide rolls into rolls of their specified widths. So for example, what you could do is you could take a 3 meter long roll, and you could split it into maybe 2 rolls that are 135 centimeters wide each, plus some spare change. Okay. Or another way you could divide a roll is, let's see, you could take this 3 meter roll and you can divide it into 3 rolls that are 93 centimeters wide, plus some change. And you could mix and match. So you could take a 3 meter roll and divide it into 1 roll of width 135 and 1 roll of 93. And I think you'd have enough left over for at least 1 roll of width 42. Okay. So how are we going to turn this into a linear programming problem? First, we're going to write down all of the possible ways to cut a single 3 meter roll into smaller widths of size 135, 108, 93, and 42, right? So we're going to write down all the ways you might subdivide a 3 meter roll. And we only need to consider subdivisions that have gaps of at most 42 centimeters wide that are left over and wasted, okay? So the first thing that we could do is we could have 2 times 135. Okay, so we could divide this 3 meters into 2 widths of 135 centimeters each. Let me cheat and go down to the answer. So we could cut out 2 widths of 135 each, or we could have a single width of 135, a single width of 108, and a single width of 42. We could have a single width of 135, single width of 93, single width of 42 centimeters, etc. Single width of 135, and then 3 rolls of width 42. So that would be like, 135, and then we have 42, 42, 42. Okay. We could have 2 cuts of size 108, and then 2 cuts of width 42. That's this one right here. Okay. These you're going to generate by computer. So you're going to write a short script that goes through and enumerates all of the ways of dividing 300 centimeters into these fixed widths, plus leftovers that are at most 42 centimeters, our smallest width in our order. This is actually quite commonly done. So it's quite commonly done that you'll make a linear program first by writing another program that's going to help you find all your constraints and your variables, as you'll see. Okay, so we are now going to let xj represent the number of rolls that are cut using, this possible way, pj. So p11 is a way we could cut our roll. 1 width 93, 4 widths 42. x11 is going to be the variable representing the number of rolls that we want to cut using this pattern, p11. Does that make sense? So x11 is how many rolls do we want to cut in this form? 1 of 93, 4 of 42. x12 is going to say how many rolls do we want to cut by pattern p12, where we just have 7 rolls of width 42 plus remainder. Okay, so our task is to minimize the sum of the xj's. x1 is a particular way of cutting a roll. x12 is a particular way of cutting the roll. Sorry, x1 is the number of rolls you cut in this way, p1. x12 is the number of rolls you cut in this way, p12. So we're trying to minimize the sum of the number of rolls needed. So this is the total number of rolls that are needed to satisfy Laurel Elementary School's order. Subject to, we have constraints. We need to make sure we give them enough rolls of width 135, etc. So okay, here's going to be our first constraint. Our first constraint says we need a certain number of rolls of length 97. Sorry, of width 135. We need at least 97 rolls of length 135. How do we get rolls of width 135? These are the ways we can get rolls of width 135. So if I cut a roll using x1, using pattern p1, I get 2 rolls of width 135, right? So twice the number of rolls I cut by pattern p1 plus the number of rolls I cut by pattern p2 plus the number of rolls I cut by pattern p3 plus the number of rolls I cut by pattern p4. The expression on the left is how many smaller rolls I get of width 135, right? I get 2 for every roll cut by this first pattern and 1 for every roll cut by pattern 2, 3, or 4. So on the left, the number of rolls of width 135 has to be at least 97. Okay, so our next constraint will be coming from this. So we need at least 610 rolls of width 108. Okay, so something's going to have to be at least 108. That something's going to be the number of rolls we get of width 108. And that is x2. This pattern P2 gives us 1 such roll. I'm looking for 108s plus 2 times x5.
Excuse me real quick. I think you meant to have 610 instead of the 108 on the right-hand side.
Patrick, you saved me. Thanks. Yeah, we want the number of rows of width 108 to be at least 610. P2 gives me a single row of width 108. This pattern 5 gives me 2 rows of width 108. So the number of rows I get of width 108 is going to have plus 2 times x5 in it. And then I have a plus x6. And then I have a plus x7 and plus x8. All right, so on the left-hand side, that's exactly the number of rows I get of width 108, and it better be at least 610. We'll just do one last one. So this last one is going to give us constraint where we're going to need at least 395 rows of width 93. From pattern 1 and 2, I get 0 rows of width 93, but from pattern 3, I get 1 row. And then from pattern 6, I get 2 rows of width 93. From pattern 7, I get a row. From pattern 9, I get 3. And then from pattern 10, I get 2 rows. Okay. So on the left of our constraint, that's the number of rows I get of width 93. And on the right, I'm saying I want at least 395 of them. Okay, so I've again cheated, and here are all of your constraints. You know, we're saying we want 97, 610, 395, and 211 rows of the appropriate size. 97, 610, 395, and 211. Okay. So the moral here is that you often use computer programs to help you write down a linear programming problem. You can sort of brute force go through and ask a computer program to produce this computation, which is telling us here how many variables we have, right? And then you have this computer program write the linear problem that then gets solved. And you can do this quite quickly. When you solve it, you find that your optimal solution is not integer, right? So the number of rows we want to cut by pattern 1 is 48 and a half, right? So the easiest thing to do here is to round up, right? Do 49 rows by pattern 1 and do 207 rows by pattern 5, okay? Do 198 rows by pattern 6. That's the easiest thing to do. It raises a very interesting question though. What if you want to optimize only over all integer solutions, okay? So what if we want to find the optimum, the cheapest way of doing this, where we specify that the number of rows cut by pattern 1 or by pattern 5 or by pattern 6, etc., are all integers. You might actually do better than if you just find this non-integer solution and round up. And so this is motivating integer linear programming. You know, integer linear programming is much harder in general, but their algorithms exist. And there, from the very beginning, you're only looking for solutions where the variables are integers. So yeah, it turns out that in our final solution, we're only cutting using 3 of our possible 12 patterns. So we're only cutting using pattern 1, 5, and 6. And those happen to be sufficient, even optimal, as the best way of getting our elementary school the sizes they need. Questions?
So when we're doing integer linear programming,
yeah.
So would we take this data point and then look at like the hypercube surrounding it, like on the coordinate axes? Like in 2 dimensions, I would look at like the integer square surrounding it, for example.
Sure. That's the hack. That's the ad hoc approximate solution. Okay. The optimal integer solution does not necessarily need to be anywhere near the optimal non-integer solution. Okay.
I don't like that.
You don't like that? So it's cool math. So the book that we're following, Matoušek and Gärtner, we're currently in section 2 of that book. It goes straight from section 2 into section 3, into chapter 3. And I think chapter 3 at the very beginning, they give an example of this. We're sort of going to skip chapter 3 and come back to it later, integer programming. But they talk about it right away. So it's a good heuristic when you're trying to find an integer solution to find a non-integer solution and round, but it's only a heuristic. For some problems, that's a provably good heuristic, and maybe you can use it to find the optimal, but for other problems, you can't. Yeah. Other questions?
Hey, Henry. So
yeah.
Right now we're minimizing the number of roles that we're purchasing.
Yeah.
Is there a way to change this algorithm to instead minimize the amount of waste we're producing?
Oh, cool question. Right. Okay. I think those two are going to be pretty closely related just because, the number of roles times 300 is equal to sort of like the amount that's being used plus the amount that's being wasted. So, within this integer subtlety, are we looking for an integer solution or not? I think those two questions are very closely related, right? We're minimizing the number of total roles, and I think that's minimizing the waste.
Would the waste problem be the dual of the original problem? Or
It wouldn't be the dual. The waste problem I would write the waste problem as sort of like, let's see. The waste problem, I would change this minimization, right? Instead of minimizing the sum of the xj's, we're going to change this to minimize the waste somehow. You're sort of changing the optimization, but I think when you write down what it means to minimize the waste, it's going to turn out to be something that's equivalent to minimizing the number of roles.
Are we just sort of like weighting the XJs by the amount of waste they produce?
Oh, there you go. Okay. Thank you, Shannon. So yeah, I was wrong on my answer. Lander's right. We need to great. Okay, Lander, thanks. You've gotten me closer. Shannon, great question. So the minimize waste problem, minimize waste. It should be something as the following form. I'm going to write a WJ XJ, and WJ is going to be the waste of each of the modes of cutting. Thank you. So like the first way of cutting has a waste which is equal to 300 minus 270, which is 30. Okay. And the second way let's do the last way. The last way of cutting has a waste which is equal to, 7 times 42. Okay, great. That's the waste of the last way of cutting. Cool, so Shannon, you've given us a different, very awesome optimization problem. We're trying to optimize this function instead of that. Yeah.
The waste on the last, the waste on the last one would be just 6, because 7 times 42 is 294.
Cool. Okay, yeah, so Lander and Shannon are totally right. The minimized waste problem is a different problem. You can see that it's still a linear programming problem, right? But our variables, our different modes of cutting, are weighted based on how much waste they produce. And I like this. This is the green company, right? This is what we should be optimizing, not what companies actually optimize.